So in this lecture series, what I'll do is I'll try to give you some more intuition behind what is wave function and what is Schrodinger equation. Okay. So what we'll do is to understand this particular Schrodinger equation, I'll try to use our wave equation and wave theory that you have studied already in your plus two. For example, you remember wave equation, you remember wave differential equation, all these things. So we'll make small analogy to all those things and interference and etc. So let us take a look. Okay. So I hope you have remembered our last lectures. In the last lecture, I have discussed a lot of things. For example, I was discussing about interference. Okay, and let us make the derivation. Okay, so this is a simple plus two derivation that you have already studied. Okay, so let us look at the derivation again. So consider you have a beam of light coming and passing through two slits S1 and S2. What happens? There is an interference pattern on the screen. Now, to calculate the intensity at P, the value of intensity at P. Okay, so now remember, since this is an interference equation, the interference is same for all the bright fringes. Agreed? This is the beauty of interference. In diffraction, the intensity was different. Remember what was the diagram for diffraction? For diffraction, the diagram was like this. The intensity was higher at the center and it went on decreasing on the sides. So this is for diffraction. However, for interference, the intensity is same on both sides of the center. Agreed? Now, how to calculate the intensity? For example, this is what we actually observe in the experiment. This is the thing we observe in the experiment. So what do we observe? We observe that when you pass the light through the two slits, there is a bright and dark fringe. Remember, I told you about the bright and dark fringe. And interestingly, the intensity of all the bright and dark fringes were same. Agreed? So this we have to prove mathematically. So how we did it? Let us see. So consider two waves, E1 and E2. So these are electromagnetic wave and I'm considering the electric field wave equation. Now you'd say why the electric field? Because light is electromagnetic wave. So many people just do this also. So many people write y. Remember the wave equation? Y is equals to a sine omega t minus kx. This is the famous wave equation that you study. But this wave equation is usually used when you are considering a simple wave equation. For example, consider a wave on a rope. So when you are considering a wave on a rope, then a is the maximum displacement and y is the displacement at any position x and at any time t. So detailed discussion about wave equation is there in our wave and oscillation CD. So you can look at that. So we don't have time to do more details of wave here. So what we do is to calculate the intensity at point P. Okay, you need to calculate the electric field at point P. So you need to calculate the electric field or the amplitude at point P. Now how to calculate the amplitude? Simple. Wave equation says, hey, there is an amplitude of E1 with respect to S1, that is the light coming out from S1, and there is an amplitude E2 for the light coming out of S2. All you have to do is you have to add both the amplitude here. So if you add both the amplitude, you will get the total amplitude E at point P. Now, are the amplitude from S1 and S2 same? No. The wave equation has to be different because there is a phase difference. Remember the phase difference? Let me remind you. So if you have a two slit, agreed, and if you have light coming from here and light coming from here, then remember if d is the distance between two slits, then the path difference, so the path difference is the black one. Let me do it sky. Okay, so this is the path difference. Look, this is the path difference. Okay, so what is this path difference? This path difference is d sine theta. You can look up the interference from your plus 2 book and you can look at this. So hence, because there is a path difference, there will be a phase difference. So remember how path difference and phase difference are related. So phase difference is always 2 pi divided by lambda into the path difference. So the path difference is d sine theta. So you understand that there is a path difference between the wave coming out of S1 and the wave coming out of S2. So there is a path difference. Since there is a path difference, there will be phase difference, and that phase difference is reflected here in the form of phi. Now you tell me, where are the minus kx? Not required. If you, even if you put minus kx here, everything is going to be same. Now to avoid writing minus kx again and again and again, so what I did is I just didn't write the minus kx. In the end, what you can do is you can put the minus kx here in between. So here, and in the end, the entire minus kx will come here. Agreed? So, and at the end it will look like a wave equation. So let us not concern with that. So it's okay if you can delete the minus kx and do, so that I don't have to write the minus kx again and again. So that's why I didn't write. Okay, so our aim was to calculate the net amplitude at point P, or total electric field at point P. So what is the total electric field at point P? You just add the electric field at E1 and E2. This is what our wave, um, how the wave behaves. You can add waves. Remember the chapter wave equation? We have already studied that. You know how you can add waves to get the resultant wave. Okay. Similarly, we added waves here. Now remember the formula for sine a plus sine b. You get a multiplication. Remember, sine a plus b by 2 into cos a plus a minus b by 2, something like that. So when you use that simple trigonometric equation, you reach to this equation. So this equation is saying this is the total amplitude at point P. But we can do one more thing. So we know that square of amplitude is your intensity. So we can calculate the intensity just by squaring the total amplitude at P. So squaring the total amplitude at P gives me the intensity at P. P is any point. P is any point. Now comes one more interesting thing. So this sine square, this thing can be averaged out. Okay, so I'll not discuss that what it means. I hope you read that in your basic plus 2. So you can find the averaged out value. The averaged out value is what? Half. So then what happens? You are only left with the cos square term. So how does the intensity for an interference pattern look? The intensity for an interference pattern looks like a cos square term. So as you can see, this is the graph for cos square. Agreed? Agreed or not? This is the graph for cos square. So mathematically, we also got that the experimental result, which is the intensity is same and depends on a bit cos, we got that same result mathematically. Agreed? So what we have done here is, instead of writing phi, we have used this relation and we have written the entire intensity equation in terms of path difference. That's a different thing. It's okay to write in terms of path difference. So either you write in terms of phase difference, that is at the top, or at the bottom you can write it in terms of path difference. So this is how intensity is calculated for the interference of light. Now you say, why are we studying this? It is because I hope you remembered our last lecture. In our last lecture, we will trying to compare many things. So what were the comparison? The first comparison is that the probability in quantum mechanics is related to the intensity in the classical interference, wave interference. Okay, so probability in quantum mechanics is related to the intensity. Now when probability is related to intensity, we know that intensity is nothing but square of amplitude. So there has to be an amplitude. So what is amplitude? Remember wave equation? Y is equals to a sine, okay, omega t minus kx. I'm not writing it. So this is a wave equation. So what is a? A is the amplitude. So what is amplitude? Amplitude is the maximum displacement of the particle from its mean position, and y is the displacement of the particle at any position x and at any time t. So why not write it down so that So I can write it as omega t minus kx. So you see that in wave we have something called as amplitude, and square of amplitude is your intensity. Okay, this is what we already know, and everything fits perfectly, because just by adding the amplitude and then squaring the amplitude, our theoretical data of interference formula matched with the experimental data. Agreed? So when probability is related to intensity, okay, then what in quantum mechanics is related to amplitude? That is the psi. Agreed? So we are doing analogy. So in quantum mechanics, the probability is same as the intensity. So whenever you are talking about probability, you are actually indirectly talking about the intensity. And when you are talking about the wave function, then indirectly you are talking about the amplitude. But there is a subtle, not subtle, but there is a big difference. The big difference is you can imagine the amplitude in the normal classical equation. For example, if I have a rope and if I generate a wave on a rope, then hey, look, you can easily imagine this rope, you can imagine this rope moving, and you can calculate the amplitude. So this is y, even this can be y. So you can calculate y, because y is nothing but amplitude. But unfortunately, in quantum mechanics, this wave function psi is complex. So once we have already proved in our last lecture how psi is complex, so you cannot imagine psi. You cannot draw psi on pen and paper like you were able to draw this electric field. But you know what psi is. Psi is somehow analogous to amplitude, and the square of psi would represent the probability, because we know that square of amplitude represents what? It represents intensity. Similarly, a square of the amplitude analogous psi, because psi is analogous to amplitude, the square of amplitude of psi will give me the probability. So this is a subtle difference between the classical wave theory and quantum theory. Agreed? Now once that you understood this thing, let me just tell you, let us go one more step. Just one more step is the amplitude in our classical theory, the amplitude of wave. So for example, I'm talking about this y, which is y is equals to a sine omega t minus kx. Can you tell me what is the differential equation that y follows? Yes, yes, can you guess? Yes, the wave equation. So the differential equation that y follows classically is the wave equation, which is dx dy square by dx square equals to 1 by v is the velocity of the wave, so 1 by v square with d square y by dt square. Agreed? So the amplitude in the classical wave theory satisfies the wave equation. Similarly, in quantum mechanics, the psi, which is the amplitude, it actually satisfies the Schrodinger equation. So we have I del psi by del t, okay, equals to minus h cross square divided by 2m. So we have discussed in detail from where the Schrodinger equation has come in our last lecture series. Okay, so I'm not going through that unnecessarily. So this is Schrodinger equation. So I hope you understood what Schrodinger equation is. So like the amplitude, so like uh, the amplitude in the classical wave satisfies the wave differential equation. Similarly, the amplitude in quantum mechanics satisfies a complex equation called as the Schrodinger equation. Please understand that the solution of wave equation is real. Agreed? So, although um, the solution of this wave equation are complex, but those complex have a real part, and the real part plays the main role. Agreed? So nearly we can get positive real solution from the wave equation. But from Schrodinger equation, you will always get complex amplitudes, or the solution of Schrodinger equation is always complex. We have discussed in our last lectures. So you see, any wave function is analogous to your amplitude in the wave interference, although you cannot imagine the wave function. That's a problem because wave function is complex. Like the amplitude in the wave interference satisfies the wave equation, similarly in quantum mechanics, the psi that behaves like an amplitude satisfies the Schrodinger wave equation. Agreed? So I hope you got an intuition behind why Schrodinger equation is also called as a wave equation, because it is somewhat analogous to the wave equation we have studied in our plus 2. Agreed? But a little bit of difference is there that I've already discussed. Now in the next lecture, we'll talk a bit about wave function and Schrodinger equation a bit more. So as you continue listening more and more of this lecture, you'll have a clear view of what quantum mechanics is actually doing. Agreed? So we talk more on the next lecture.